Here we are going to see how a beam is going to behave when there is a thermal loading. Thermal loading, thermal loading such that at the bottom we have 25 degrees Celsius and at the top of the beam we have 40 degrees Celsius, and there is gradual changes within the beam, within the depth of the beam. And here this beam, here beam 1 is subject to thermal loading and beam 2 is normally nature. So here you can assume there is 2 room, okay, and fire incident occur somewhere high temperature such degrees Celsius, and at the bottom you have temperature 25 degrees Celsius, and room temperature is your 28 degrees Celsius. Now here we are going to see how the beam is going to deflect and what will be the shear force bending diagram when the beam is subjected to only thermal loading. Here you can see there is no active loading acting here in the beam. There is no idle loading, there is no moment, there is no point loading in the beam. The temperature rises will cause axial deformation as well as your bending deformations. Okay. So we're going to see how you can solve this problem. Now, before jumping to the solution of this problem, let us first discuss the basic part. We already know. Let's discuss the basic part. We already know that change in length is equal to alpha delta T times L, or alpha, which is your thermal coefficient, that is your delta L by L by delta T. That means that is your fractional change in length, that is delta L by L by delta T. Okay. So fractional change in length, unit temperature changes is called your coefficient of thermal expansion. So now, if we see that delta L by L is your strain, so here we can write that alpha is equal to, alpha is equal to 10 times delta T, or you can say the strain is equal to alpha times delta T. Again, we know the stress is equal to E times strain. From there, you can write stress is equal to E alpha delta T. And if we know that area, if we know the cross-sectional area, and if we multiply with that area, we can find how much axial force is developing. Okay, we can calculate how much axial force is developing. Okay. So for the axial force, which will develop due to the temperature changes, that is equal to EA alpha times delta T. EA alpha times delta T. The axial force that will develop due to the temperature rise, that is your EA alpha times delta T, and moment which is going to develop due to the differential change in the temperature, that is your EI by D times alpha times delta T. Here we have EA, but here we have EI by D. D is your depth of the, E is your depth of your beam. Okay. Now here delta T for axial case and delta T for moment is defined. For axial case, the delta T here, your average temperature T mean minus T room temperature. Okay. So here room temperature is your 28 degrees Celsius and mean is your mean of 40 degree plus 25 degrees Celsius, that is equal to 2.5 degrees Celsius. For moment case, this delta T is your temperature at the top minus temperature at the bottom. That means 40 degree minus 25 degrees Celsius. Okay. So now we have learned what is the axial force going to develop due to the temperature rise. There is the moment is going to develop. Moment is going to develop due to the temperature changes. So we are going to solve this equation. F is equal to K times U plus force acting as a fixed end. If the forces are acting in the node, okay, all the forces acting in a node, in that case, you'll observe that this part is going to be 0. If the forces are acting in between the element, in that case, need to convert all the forces into the node, equivalent node. Okay, that is basically your fixed end action of fixed end forces. Or other way you can say that is your equivalent nodal forces. Whatever the load is acting here, that load basically we are converting into a equivalent nodal forces. So here, what we are going to do, you observe that there is no active force acting in the beam. Well, you can see there is no active force. Acting in the beam. So active force is 0, and due to the temperature rises, there will be axial force as well as your bending moment. That is basically that we need to convert into the equivalent nodal forces, or other way you can say that equivalent to, or other way you can say that your fixed end action. Okay. Now we are going to solve this problem considering frame element. So if you consider frame element, that means the size of the stiffness matrix for the frame element will be 6 by 6. So here you see that first column is corresponding to the axial degree freedom. Here you can see this is your first degree freedom, second degree freedom is corresponding to the vertical translation, third degree is corresponding to the rotation. Okay. Similarly here, fourth degree is corresponding to the axial translation, fifth degree corresponding to the vertical translation, and sixth degree is corresponding to the rotational degree freedom. Okay. So here, first and fourth is corresponding to the axial degree freedom. Okay. 2, 3 and the 4, 6, 2, 3 and the 4, 6 correspond to the BMD event. Okay. Now, if we calculate the values, okay, if we put the value of AE and the L, or EI and the L, you can calculate all the values. Okay, you can calculate all the value of the stiffness matrix, and you can get the stiffness matrix for the element 1 like this. Okay, so here if you put the value here, obtain the stiffness matrix for the element 1, size is your 6 by 6. Okay. Similarly, for the second element also, you can calculate the stiffness matrix, which will be of size of 6 by 6. And degree of freedom for the second element is 4, 5, 6, 7, 8, 9. So here, the global degree of freedom is 4, 5, 6, 7, 8, 9. And local degree of freedom here 1, 2, 3, 4, 5, 6. So for each element, local degree of freedom will be 1, 2, and 3. Here will be 4, 5, and the 6. So local degree of freedom is here 1, 2, 3, 4, 5, 6. And corresponding global degree of freedom will be 4, 5, 6, 7, 8, 9. Okay, now what we did, we obtained stiffness matrix for the element 1 and the stiffness matrix for the element 2. Now we can assemble it and we can obtain global stiffness matrix Kg. Okay, so Kg will be size of 9 cross 9. Okay. So here you can see for the element 1 we have 1, 2, 3, 4, 5, 6. So up to 6 we will have the K1. And for the second element, degree of freedom started from 4. So here from the 4th degree freedom, again we will have the second stiffness matrix A2, this part. Okay, and here you can see degree freedom 1, 2, and 3, and degree freedom 7, 8, 9 do not have direct relation. So this value is going to be 0. This value is going to be 0, and stiffness matrix is your banded. You can see stiffness matrix is banded in nature. It is symmetric with respect to the diagonal term. Okay. This banded means here you can see the band is symmetric with respect to the diagonal, and all the diagonal terms are positive. Okay. Now here we obtain the global stiffness matrix. Now we have to find the fixed end action. Okay, so already we have discussed that if there is a temperature rise and the temperature rise is not uniform, the temperature rise is non-uniform in nature, then that will cause axial forces, resistive forces, as well as your bending moment, that we are saying fixed end action here. Okay, and that value will be AE alpha times delta T. Here delta T is corresponding to the mean temperature minus your room temperature. Okay, so A value is known to us, E value also known to us, alpha also is known to us, and here delta T is your 32.5 minus 28, and that will be 432 kilonewton. Similarly, we can calculate the fixed end moment that will act here, that will act here, that your fixed end action, and that value is your, that is EI by D alpha times delta T. Okay, M is your EI by D alpha times delta T. E is here 2E. Okay, I value is known to us, D is here 0.128, alpha is known to us, and here delta T is your temperature at the top minus temperature at the bottom. If you calculate, you can find what value is coming 178. That value is coming 19.78 kilonewton meter. Okay, so here axial force is 432 kilonewton, and moment is here 7. Here moment is here 19.78 kilonewton meter. Here for this element, moment is 19.78. This axial force, that is your accelerating force on 432, and here 19.78, and axial force here 432. Okay. Now that value we can write in a vector form like this. So here we'll have a vector size of 9 plus 1. We'll have the forces at degree freedom 1. Here this part we are writing in this direction positive. So at 4th degree, this will be your negative in nature. And here the moment here we are writing it as a minus sign 19.78, and here position 19.78. Okay. And rest of the value are 0. So here we do not have, here we will not have any forces which is acting vertically. Okay, there will not be any resistive forces acting or developing vertically. So all the values are 0. Here in this node, since there is no temperature rise here, the second element, all the values will be 0 here. Okay. So now what we did, we obtained the stiffness matrix Kg, and we obtained the force vector. Okay, force will be basically equivalent nodal forces or fixed end action force. All active forces are 0. Okay. Now we can apply the boundary conditions. Here we just see this end and this end are fixed. Okay, so all the degree freedom are still for the node 1. So here degree equation 1, 2, 3, and 7, 8, 9 are fixed. So we apply the boundary conditions, and here we have to eliminate that particular row and the particular column from the stiffness matrix. So here we eliminate this column and this row. Here this column and this row. At the end, we'll have 3 by 3 size of reduced stiffness matrix. Okay. Now, if we apply the boundary condition in the forces, so here 1, 2, 3, 7, 8, 9 will be eliminated. So here we'll have 3 size. Okay. Now we'll have stiffness matrix of size 3 by 3. We'll have that force corresponding to the fixed end action, that is 3 cross 1, and this is 3 cross 3, and this part is 0. Now we can solve this case and we can obtain the displacement quantity. Okay, so here we can solve it and we can obtain the displacement quantity. Okay. We solve this problem. So here we'll have the stiffness matrix after applying the boundary conditions with the force vector after applying the boundary conditions. So here we are going to solve this equation. We are going to solve this equation, and you will observe the displacement quantity is coming your U4, U5, and U6. So here we'll have displacement quantity. Okay, U4, U5, and U6. U4 is corresponding to the axial deformation. So here this node is going to have displacement in this direction. That amount is your 1.44 mm, 0.144 mm, and vertical displacement is coming your 14795 mm, and we have the rotation here. Okay. Now, if we want to plot the displacement quantity, so here you observe that displacement is coming, vertical displacement is coming in the negative term. So here this point need to go upside like that. Okay. And here you observe the displacement pattern. Here observe that you observe that our rotation is coming minus. So here that negative rotation, that means displacement or rotation, that means rotation will be clockwise. To maintain that, the beam is going to deflect like this. Like this. So here, this is your negative. So here, you can draw the tangent here. Draw the tangent here. Yes. So here, this is your clockwise. Like this. And that rotational value is your minus 719 to 10 to the power minus 6 radian. Okay. And U5 is negative. That means this point will try to go upside like this. So here, if you have non-uniform temperature, then the beam is going to bend like this. Okay. So now here we'll see, we try to plot the shear force and the bending moment diagram. Then again, you have to solve this equation where we have FEA that is known to us, kg also known to us. The size of kg is 9 cross 9. This also will be 9 cross 1, and this will be 9 cross 1. We know the value of fixed and action force. We know the value of global stiffness matrix. We know the value of U. U means U4, U5, U6. So here our U will be of 9 cross 1, but this value will be 0. And here we have U4, U5, U6, 0, 0, 0. Okay, 9 cross 1. U will be like this. Okay, and if you put the value, we can find the forces developing here. Okay. Forces developing here. You could solve this equation if K times U plus fixed and action. So here K The global K, kg, that side is 9 plus 9, and U will be of 9 plus 1. That the 0, 0, 0, 0, so that is 7, 0, 8. It is also will be 0, 0, 0, side 0, 0, 0. So you also do 9 inside 9 like 9 plus 1 plus 1. Fixed and action already down to us. If we now if we solve this equation, now if you solve this equation, if K times U plus F E A, okay, then and the reaction force. Here we observe reaction forces coming like this. Here, axial force equal Newton. Here, Q2 equal 6 kilonewton. Right. Here also 6 kilonewton. So, comment here 9 kilonewton. So, here we have vertical force equal 6, axial force 134. So 5 times 39 kilonewton. Now, on to draw the shear force as a minimum diagram. Observe. Now, if you want to plot the shear force on a minimum diagram, then you observe the shear force diagram is rectangular in nature. That indicates that everywhere shear force is constant. So here that value will be your 3.6. So 3.6 and here also 3.6. Now, if you want to see how the bend event look like, observe that at this fixed end, the moment value is your 23.38, and the other end, it will be your 5.39, and if we connect this point, the variation is like this. Then here, that value will be 9 kilonewton meter. 23.38 and here 5.39. Now, if you see the deflection pattern, already I have discussed that the beam is going to deflect like this. Here it will have zero displacement. So here we have a straight line, and then we will try to go up like this, and then it will go down, and again here like this. So here the slope tangent here, you can see tangent, draw tangent here, that slope here for the 3-degree freedom. That value was 719.3 into 10 to the power minus 6 radian. Okay. And displacement here, that is your U5, that value is coming 0.4795 mm. Okay, so here we have seen that if a beam have a non-uniform temperature rise, then there will be axial force as well as your bending moment. Okay, and here we have learned how to get the deflection pattern, how to obtain our bending moment diagram, how to obtain our surface diagram. Thank you.